Isso aí é tradicional, 5, 10 minutos, né? Mas depois, bom, ele vai fazer, depois a gente dá com passo. A única minha instrução é, né, eu digo, você tem que chegar na 15 de 5. Você tem que sair daqui no limite umas 4. Top. Aí, né? Certo, aí a gente consegue melhor. Aí só programa tudo, tem as aulas na quarta-feira, se quiser ver no blog, esperar que as coisas não fica aqui. É mais uma variável que tem lá no sistema. É certo, tem jeito. Chegou o cara aí. Você já volta para as 7 de volta da assim, paulistano, né? Sempre. Então aí tem que fora um tempo, depois foi 7 anos em 7, agora está 7 que gosta. E o povo gosta, pô. O povo gosta. Contrato em cima de contrato. Foi 10 anos. Esse inteiro, assim, não sei ver. Bicho. Nossa, o que está vindo aí? Está enrolando, não está vendo. Depois faz um blá blá rapidinho depois. Não presta atenção que vai. Não entra já pergunta. E daí. Vai ficar rapidinho. E aí está. Eu tenho lá, eu tenho que ficar feito. Então, mais 4, na verdade, vão gerando, que vai saber trem. 5 reunião assim deve ser com
tá no mudo. Agora já pode ligar. Boa tarde a todos. Hoje a gente tem prazer de receber aqui o Dr. Paulo Simões. Muito obrigado por aceitar o nosso convite. O Paulo Simões é um físico solar com mais de 20 anos de experiência em estudos de flares solares, usando dados de multicomprimento de onda, desde raios em rádio desde ondas em rádio até raios gamas e simulações. Atualmente, ele é professor na Universidade Presbiteriana do Mackenzie. E também pesquisador no Centro para Radioastronomia do Mackenzie. Obteve o seu mestrado em Astrofísica em 2005 e o doutorado em Geofísica Espacial em 2009, junto ao INPE. Muito obrigada. Hoje ele vai falar um pouquinho sobre os flares solares e estelares. Ele vai falar em inglês, né?
Em inglês. Angela, brigadão pelo convite. O som tá... Tá. Agradeço o convite antes de passar para o inglês. Né, como a gente falou, apesar do feriado, tá ainda trânsito, mas deu tudo certo, tá tudo em ordem, então agradeço a presença de todos. E não vou passar para o inglês, acho que fica mais geral, mas qualquer dúvida, qualquer pergunta pode ser inglês, português, a gente vai chaveando de acordo com a necessidade. Pause, language settings, English. Good afternoon, everyone. For those who don't know me, of course, Angela introduced me. I'm Paulo Simões. I'm at Mackenzie University. I do solar flares, mostly, most of the time, wavelengths all around. And as well, so that's kind of the topic here today. I wanted to talk to you. It's a kind of a brief overview of those two topics, because there's a lot to cover, so, and I will not cover all that much. And just to explain here the picture, this is a photograph that I took from our at CRAM, at Mackenzie, at the rooftop we have there. And of course, we're going to talk about white lights, and there's a nice rainbow here. Also shows how difficult it is to make solar observations in São Paulo. Beautiful sky. And I believe it's this one. Yeah. So I would like to give you a brief overview of solar white light flares, and then we move to stellar white light flares. And then, last but not least, I'd like to tell you about our new telescope at CRAN to observe white light solar flares. I'm curious, quick show of hands, how many of you know a bit about solar flares? A little bit. I heard about it. Okay, some information. Okay. This will be a very, very quick review on overview on solar flares. This is the sun as seen in ultraviolet. This is taken from space, from Solar Dynamics Observatory from NASA, and this is a cut from this region where a flare is happening, right? And here you see the eruption happening. There's brightness happening all across, and then these blue thingies are the locations of the emission from hard X-rays, tens to hundreds of keV X-rays emission. And in time, the X-rays look like this. That is the impulsive phase of flares, where the energy is being released from the magnetic fields that store the energy, is released within a certain time, heats up the plasma, accelerates particles, electrons, ions, lots of things. And the light curves show very impulsive, typically, behavior, followed by a more gradual curve from soft X-rays, or some bands in ultraviolet as well, that shows the heating of the plasma on those regions. And that's what we call the gradual phase, where most of the relaxation and the cooling off of for the energy that was inserted in that region. As you see, it's a very, very small, relatively speaking, localized place in the sun, and every flare is different. They share these common properties that I mentioned, but they're all different. They have X-rays, hard X-rays, solar X-rays, soft X-rays, ultraviolet emission, all that stuff, but they're different somewhat. Now, white light flares. That's kind of a misnomer nowadays, because technically we're talking about the optical continuum. White light flares, because of course the first observation, the very first observation of that stuff was the very famous 1st of September 1859 flare observed by Carrington and Hodgson back in the day when you had to draw your data, right? That's the flare. Carrington making observations of sunspots. So you have here the umbra, penumbra, and he saw two bright thingies appearing. I strongly suggest for everyone to go look at those two papers. They're very short, very historically interesting to read. And he saw, both of them saw a singular appearance, a curious appearance. And what the heck is that? And of course, from that, probably most of you have heard about this. About a few days later, the magnetometers on Earth went haywire or crazy. Telegraphs were catching fire or working without batteries. Auroras across close to the Caribbean, to lower latitudes, because that flare was accompanied by a very, very strong geomagnetic storm that caused all sorts of weird things in our magnetic Earth environment. We skip ahead a bit more than, well, nowadays, 160 plus years to another flare in September. This is 2017. Now we don't have to draw the data anymore. We have cameras, CCDs, and this is a white light image. It's not broadband, but get there. And the white contours show the excess of emission when the flare appears, which is kind of the same, roughly. Right? This is from a flare we analyzed a few years back. Now, other properties. Now, putting those two things together, the white light stuff, visible continuum, with the X-rays and all that. What we have here is, unfortunately, this is a paper from Watanabe, a flare. The darker stuff here, this image is inverted, is the bright stuff on the white light. And is usually, spatially, correlated with the hard emission. So with the electrons, high energy electrons, reach the surface, let's say, the lower atmosphere of the sun is more or less in the same regions where you have the white light emission as well. In time, this is back from the other event, but to give you an idea, in time, the white light also correlates with this impulsive phase, right? The soft X-rays show the heating in the corona. The UV spectral lines or visible lines show heating or related to all the heating and collisions to get ionized states for different elements and all that. And the white light shows like this. It's kind of impulsive-ish and follows us as well with the infrared terahertz emission that is a kind of new-ish band of observation for solar astronomy, pioneered at CRAM, the Mackenzie. And lastly here is microwave emission, which tracks well with hard X-ray emission, showing the particle acceleration process that happened there. So that's kind of a general overview. But if you want to understand the white light emission itself, the continuum, then we need spectra. Okay, let's go back in the past. How much of that data we have? Not much, a little bit. That's all from the 60s, 70s, 80s, before the digital age, so no CCDs, it's all film. Right? So we have 3 flares here, right? From those guys here, for Neidig, Hiei, Machado, and Rust. And see those points of the data, the line is just a kind of a fitting, it's not a model. And usually, see the Balmer limit is around here, the recombination of hydrogen to level 2. And it kind of, okay, oh, there's something here. There's something here as well, but it's kind of in the wrong place. Nothing here. Okay, interesting. Another event or another flare here with more data points. But it's noisy. See the Balmer lines, the high order Balmer lines popping up here. It's interesting. Okay, cool. But that's it. There's a handful of spectra observed from flares. It was difficult. It's really, really, really difficult to get flares, flare observation spectra back in the day of film. It's really hard. But from that data, people start to realize, okay, what's going on there? And this is not a model fit, it's just showing the ideas, right? Got the Hiei data. We show that kind of Balmer jump relationship there. And people came up with 2 ideas. Okay, so that should be, that step should be indeed related to the Balmer jump, so recombination of hydrogen. When electrons recombine to hydrogen, they emit energy, and they'll give you this very specific spectrum shape. But it doesn't quite match the difference here for the Balmer, so they had to come up with another idea. Okay, maybe this part would be the area, the region of the Paschen continuum, and say, oh, that might be a blackbody spectrum. If you heat up the photosphere, it gets hotter, so it gets brighter, so get more emission. bunch of papers since the 60s, 70s, 80s discussing those ideas. So would they work? Well, even from the 70s, we say, okay, we discussed that there we have electrons accelerated. Those are the main, is the main process to deliver energy from the magnetic region, magnetic reconnection region into the chromosphere. Now, the electrons, of course, have to go from up. This is the height in the atmosphere. This is a simple model of the atmosphere of the sun. When you have temperature, right, the base of the photosphere, temperature minimum region, chromosphere, into the corona. Electrons have to go this way. And depending on the energy, depends on it tells us how deep they can go. 10 keV electrons, yeah, they can go that far. 100 keV electrons, yeah, they kind of get close at the base of the chromosphere. It's not possible to get high energy electrons into the photosphere to deliver that required amount of energy to trigger a black body emission that's needed from that data. So it's a problem. Now, then people came up with a different idea. Maybe what's happening there is, now we're upside down, okay? Sorry, it's on the side. So it's not on the side. So electrons come from the top, reach the chromosphere, hit up things. You get all sorts of spectral line emission, Balmer, continuum, all sorts of cool stuff happening in the ultraviolet range. And that radiation shines up and goes into the photosphere, is absorbed there, hits up the plasma, then you get the black body emission. Doesn't work. Right? That's the back warming idea. Lots of people did some calculations. It hits up a bit. That's it. Not much more. There's a problem there. But we don't have data. Well, maybe now we do, because now we have CCDs and nice spectrometers. Well, not really. Those are the three main observations that we have that cover the continuum in broadband range somehow. Karen Fletcher, they have 3 points, RGB, 3 points in the visible spectrum. And they try to fit the model, to the data with the two models, the black body and the recombination continuum, both work. Okay, so that's inconclusive. Great. There's another one by Client, Lucia Client. They also have 3 points, but one is in the far ultraviolet, one's in the optical, one's in the near infrared. Recombination continuum, black body, then neither work within the simple assumptions and all that. And there's one by people in Montreal Observatory, Czech Republic. They have 2 observations of flares. You see all the Balmer lines and everything is nice, but they never calibrated their data. So we can't do much with that, right? Okay, so we don't have data. So let's look at models, right? Kind of sidestep here. This is what we did a few years ago, that where we employed relative hydrodynamic observations, simulations. It's a 1D model, so the atmosphere is one dimension. You put temperature, electron density, proton density, all that good stuff, and then dump energy into it, shooting electrons into that atmosphere, and let it evolve, considering all the hydrodynamics and ready transfer information of spectral lines and all that, and see how that one, of course, feeds into the other, and let that thing evolve. And from that, you can see how different emissions can happen during a flare. Now, this one, right, here we have a snapshot of, hopefully the movie will play, but you have the energy input. Everything is, from the left, is based on the photosphere up to the top of the chromosphere. Energy input, the temperature, ionization of hydrogen, electron density, and I'll mention this to you in a bit. Right? And the gray stuff here is the quiet sun, is undisturbed atmosphere. Right? So you can see, for instance, where the photosphere, chromosphere, and the corona are. So hopefully this will, yes, it works. Right? So you see that the energy is deposited at atom height. Different mean slightly different models in terms of parameters of electrons. And here it doesn't matter that much. But the cool thing is, energy goes in, heats up the plasma, ionizes hydrogen very quickly, that gives off extra electrons into the environment. And in this case, we're looking at the infrared terahertz emission range. And that increases the optical depth in that range. That gives the extra emission for flares. This is the contribution function that essentially shows where the emission is coming from. Right? So you have the quiet sun here. So the main emission is coming from the photosphere. So if you look at an image in infrared, it looks like the photosphere. Spots and umbra, penumbra, and all that. But the flare is not happening in the photosphere. It's happening in the chromosphere because of that excess of electrons. And this was, so we thought, okay, so we see the excess of hydrogen, of electrons coming from ionizing hydrogen, so we can look at the white light stuff, right? If the hydrogen is ionizing, you should recombine, then stuff should happen. And this is snapshot, is working preparation because of many different reasons. And this is, again, the contribution function from the ultraviolet down to near infrared, all the colors here, but showing that the quiet sun, the photosphere, is pretty much undisturbed. The flare excess pops up in the chromosphere, and optically thin for everyone. And you look into the spectrum, here's a complicated figure. I won't waste too much time on this, but the points here show the ranges of observations that we have from those flares that I mentioned before, right? From Kerr-Fletcher, from Klein, a few others, and just to show how the spectrum that we get from the models kind of fall in the same ranges from observations. We're not trying to fit observations to the fit the observations with the models. It's just a comparison, quick qualitatively comparison to see if that makes sense, and kind of does. Right? So that's the state of solar flares so far. I'm going to get through more data at the end. Now to stellar flares. There's a long history that I won't have time to go into all the details. Right? But making long story short, that interests us here is we start with Fisher 1992. They observed a flare from AD Leo, it's an M dwarf, and they managed to fit the data they had. It was the usual UBV filters, and they could fit the excess of the flare emission with a 9,000 Kelvin blackbody emission. I said, okay, cool. And they went through a whole discussion. How can you read the photosphere? The same thing we discussed already here, right? How can you reach the photosphere with the electrons? You cannot do that because of this, because of that. Okay, so they already proposed the back warming idea. You heat up the chromosphere that shines into the photosphere, cool and nice. And it only hits the photosphere by about 400 Kelvin, which is nothing for what's needed. They got more data. Susan Hall got more data from AD Leo again, and that's one of the panels from their data. They have more panels in their paper, right? The UV, the UB, the usual filters. And that's a quote from their paper. Blackbody provides only an approximate fit to the observations. It kind of fits, but it doesn't really. The issue here is that I think maybe you've all heard about the Nature Mayhara paper that did a statistical analysis, 300 something stellar flares, and came up with the idea of the super flares. The energies around 10 to the 33 to 1036 erg, which is way more than we see in the sun. And how did they get to these energies? Fitting the data to black bodies. They have one data point. That's from, got a blank. I think it's Kepler data. Yes, because too old for TESS. Kepler is one data point. It's broadband, it's visible. That's it. Right? So they say, oh, let's assume a black body, use that to extract the energy. Now, okay, it's a way to do it. Of course, you only have one data point to fit a spectral model. The issue is now you have thousands upon thousands of flares detected, many different kinds of stars, and everyone is following that model. But Now times start to get a bit wibbly-wobbly, timey-wimey, because the sequence of the papers I'll mention here are not in chronological order. But is the blackbody a good model? It's a question here. Then Wierenberger last year published a paper with GLX data, near ultraviolet and far ultraviolet data. And for a whole bunch of flares, I don't remember how many now, but 98% of your sample, you cannot fit with or explain with the blackbody model. You have too much. The ratio of the far to near ultraviolet expected for blackbody is 0.17. They got something like 0.5 to 2, the ratio. So, no, that's not a good model. Earlier this year, Adam Kowalski and collaborators with Hubble data, they had for a different star again, so Draconis here, CR Draconis, and they have ultraviolet and near and far ultraviolet data. That's the blue stuff here. That's their data. Also TESS. TESS data is here. And the 9000 blackbody, you see here, this is the blue one. So yeah, it's a bit off. They even tell, okay, some UV flares clearly show a much greater response than the 9000, 10,000 Kelvin response that a blackbody would predict. Well, then it kind of doesn't work. So they did a radiative hydrodynamic model as well. Same, not same, but the same code, but with different parameters for this event, which is the, what's this called, pinkish, that goes here, that will go through their data. Now, the issue here, the interesting part, is that they had to use energy flux 10 to the 13 ergs per second per centimeter squared, which is really high. For the usually 10 to the 11 for comparison. Of course, these are much stronger flares, cool. But the other thing is that the energy cutoff, which means here's the minimum energy of electrons present in that model, is 500 keV. It's relativistic electrons, essentially. Right? It's challenging to explain a particle acceleration process that only gives you relativistic electrons. Where's the other stuff? Why do you cut there? Right? In this case, of course, they're exploring. It's perfectly fine to do that, to see, okay, can we do this? Okay, kind of matches. But then the next question is, how can you explain this? And it's not easy. Okay? So with all that, those ideas, okay, the blackbody model is not quite fitting to the data, and we don't have much spectral coverage anyway. So we had an idea looking at the solar stuff, like, okay, the hydrogen recombination could be a reason or an explanation. So we had a very simple idea. Let's get a optically thin local thermodynamic equilibrium slab of plasma, recombining hydrogen that will give you this spectrum. So it's all analytical, very simple. And instead of using the blackbody model, use this one. And you do the same thing as people did since Maihara's time, right? 10, 12 years ago, which is basically you get the response function of your telescope, in this case Kepler, fold into the spectral model you want, and scale that with the area of the flare to get whatever is the flux you observe from a flare. That's it. That's the model. That's what people do with blackbody models, but we just changed the model, essentially. And we did this for two stars. So it's two Kepler stars. One's a K spectral type, the other one's a G. So it's more like solar type kind of stars. All the others are M dwarfs. M dwarfs are very active. Well, at least the ones that people have been looking at. So these are more solar type. And again, long story short, the blackbody model gives you some range of energies within some expected areas to explain the flux we observe. And if you change the model, then you have less energy emitted, but you need larger areas. So it's not that much of a difference in terms of all the discussions that people have been doing in the past 10, 15 years in terms of the energy of flares. That's still valid, right? You still need a lot of energy to power those flares. Well, cool. but given the lack of spectral information, or even the confusion of spectral information for those previous examples, why not? Might as well use that. That's our argument there. Blackbody kind of, how can you explain this? So use this one. Following that, our paper then, Peter Heisel from the Android Observatory came up with, oh, but you can, instead of assuming optically thin emission, yeah, you can calculate the radiative transfer and consider how is the opacity of the plasma in those ranges. So these are plots from his paper for two kinds of stars, so M dwarf kind of temperatures and G-type stars kind of temperatures. Just say, okay, maybe the shape of the spectrum can change a bit if you consider the full radiative transfer for a simple uniform slab of plasma. Okay? It doesn't make that much of a difference in our case. We're kind of the same. For the parameters we used in our paper, it doesn't change that much, but it's a good thing to keep in mind. And then there's all this challenge, how you adjust the data we have and the complexities of explaining a model. And probably the best way to do it is with those RHD simulations. That's a paper from Rowski, Allred, and Carlson last year that tried to show different examples of those models. Right? So I got two figures from their paper. So this one is just to show that the rate how you input energy as electrons into the model, just kind of a whatever that shape is, or just a constant flux of electrons, that changes how the light curves, the time evolution of the flare will appear. Of course, if you have a kind of this more phenomenological, let's say, curve, then the light curve of the continuation will kind of follow it. If you have just a constant stream of electrons and then shut them off, then you have this increase, and then it drops off. It doesn't look very realistic, let's say. Right? So that's already a parameter that you have to consider, which is complicated. Seconds, 4 or 5 seconds. You cannot run these models for like, oh, minutes. No, it doesn't work. It breaks down. Okay? But still a good way to check in terms of the, let's say, spectral quality, spectral response you get. So this is different kinds of spectral response they get. So this is the quiet emission, won't go there. But for two cases, let's say a more solar type of energy input, you have different recombination edges from different elements. But the cool stuff here is hydrogen. Then you have the Lyman edge, Lyman continuum here, Balmer continuum here, Paschen continuum, and then Fund and other stuff. And that's kind of, like I said, that's kind of solar type, 10 to 11 ergs per centimeter square per second. It's a solar-like condition. Now, close to that 10 to the 13 case, the energy cutoff here is not 500, it's 85, so it's a bit better, though that limit. You get more, a higher emission for everyone. Of course, you put more energy, you get more energy out. But then into this, the Paschen part, you start to get close to that black body shape, because essentially you ionize so much hydrogen that the plasma becomes optically thick to that region of the spectrum. So you approach the black body model in the chromosphere, not in the photosphere. So there's a lot to discuss into that. And since I mentioned the Lyman continuum here, it's cool to mention also we can see the Lyman continuum for solar flares. Won't go details, but there's there was a spectrometer in the Solar Dynamics Observatory, covered the Lyman, so large UV range that you can see the Lyman continuum, and you can see flares from there. So it's quite cool. Anyone is curious about that stuff. And, okay, like I said before, we don't have that data for solar flares, so we need to get more data. How do you get more data? You get new telescopes in shape. And here's ours, Solar UV-NIR Spectrometer. Suns, with a nice drawing that I'll mention more about it later. Right? So SUNS was born from initially a FAPESP funding. It was kind of a side tracking of FAPESP. Was that the thematic one? I don't remember. Anyway, a FAPESP project for other stuff. Then we got from GIGIS DPI, Mackenzie. Then we got this guy. It's commercial ocean optics spectrometer. The UV range from 200 nanometers to 1,100 nanometers. The spectral resolution is not great, but we don't care about that. We want to see the whole visible continuum. And given the time integration and resolution AD conversion, we should have enough dynamic range to see flares. Of course, it's a spectrometer. It's a spectrometer. That's it. And then we had what's the word I'm looking for? A contract, let's say, with Institute Steiner. Here, Chuck is here. Chuck was the designer here, the engineering design to how to fit that thing into our observing facility there at CRAM. We have a cellostat in the roof. At the roof, so we have two mirrors. One there is moving, tracking the sun. That shines the light into this mirror. That shines the light into the building, where we have a 30 terahertz camera. There's a Newtonian telescope, and with a splitter to a H-alpha telescope. And then you had to fit that guy there. So Chuck figured out how we do that. And very long story short, here, right? That's the whole design. The idea is that the light will come from here. There's a beam splitter here that with a focusing lens, we'll put the light, the sun here, where you have the optic fiber connector that will feed into the spectrometer. And the idea is that we can, given all the focus distance geometry, blah blah blah, we can see a small region of the sun. Relatively speaking, a 2 Archimedes region of the sun, so we can point to an active region and hope for flares and get good enough contrast. Because white light flares or the optical range, you need a lot of emission to get a good contrast against the photosphere. There's another view of that, our new baby there on the side of the Newtonian telescope there, and all the parts in assembly. Right, cutting the acrylic board for the cover, lots and lots of drawings. That was fun. More drawings. Right, how it looks from the side, everything go, and then start to put together the whole shape. This is a microscope, so you can see the reflected light from the sun into this, so we can see the disk of the sun and help to point the fiber with these. I think I have the better view. Yeah, with these screws to position in X, Y, and that's our boy. Go. That's SUNS. Right, with a nice cover here, so we don't get straight light in. So it shares all the optical arrangement to get light into the building. The terahertz camera pointing down here behind that piece of wood. And here the screws can adjust for the position, feed into the spectrometer, tied to the computer. And on the beginning of May this year, Thiago sent me a message. It's ready. Man, you have to, tomorrow is the International Day of Light. So we have to get first light tomorrow, right? I told you that, right? Yeah. And the sun was shining, the sky was clear, and then that's the sun in the microscope image there. The nice solar spectrum here, terahertz image, H-alpha image, and first solar spectrum with some the main lines identified here, some telluric lines, H-alpha, H-beta, magnesium lines, sodium lines, all that good stuff. But we don't care so much about that. We want to see the excess that pops up when you have a flare. And just to mention the logo, because again, it was Thiago's idea. Oh, you have this white cover. It would be nice to have a nice sticker, just with a nice image. Okay, that's a good idea. All right. I know some people did design course at Mackenzie. Some calls, some meetings, some coffees. And then we were the clients for the 6th semester class of design. So we had to go there, present our case. We would like to have a logo for our telescope. That's what we do, and so on. So the class split in 6 or 7 different groups. They made proposals for different ideas for the logo, and this was the selected one from, of course, I have to show that. Fernando was the one that designed this. It's not the final version, but it's almost there. Right? Designed this, we selected to be the official logo for our new telescope, and hopefully get flares soon enough. Right? And well, to sum all this up, solar white light flares, we still don't know what's going on there. Black body, hydrogen recombination, because we don't have enough data. We're going to solve that. White light flares, stellar white light flares, being modeled as black body, 9,000, 10,000 Kelvin black body. It works for some flares, not so much for the others, but most of the time don't have enough spectral coverage to model anything, but people assume that anyway, which breaks down for the UV bright flares. It doesn't work, right? And another thing I didn't mention before, but we're talking about different class of stars. Their atmosphere must be different somehow, from M to K to G stars. So it's not just like the sun, which is the same star with the same atmosphere, different flares, like I said, they all look like different, similar properties, but different. For stars, it's probably worse, because the star is different. Right? Given all that, we propose a simple model, just use hydrogen recombination model. Why not? The calculation is as simple as the black body model. And then, I'll say even that calling white light flares is kind of an issue, because you see, you need UV, you need infrared to actually narrow down what's happening in terms of physics. And we have a new telescope to hopefully collect data to look up white light, solar flares, and hope to get flares soon enough with the kind of peak of the solar activity cycle. So flares abundant. We just need clear skies, hope for that. And of course, if anyone is interested in collaborations for any sort of that stuff, master's, PhD, postdoc positions, calls up, and we'll be happy to have a chat. So thank you so much for your attention, and I'm happy to take questions. Thank you.
Thank you, Paulo. Very nice talk. We have time for questions.
Hi, nice talk. I'm one of those few people here that doesn't know a lot about flares. And I have a question. It's a curiosity. Yeah. And it's about the stellar flares. Now we'll have, in a few days, I think, the LSST working. And it will be monitoring billions of stars. Yeah. So how will this impact, how this will help with the constraining the physics of these white flares from stars? I know it's you have no spectrum, but you have 6 bands, I think. Yeah,
it's an interesting thing, because most of the time, it's difficult to have a telescope dedicated to solar/stellar activity, right? Kepler, CoRoT, TESS are not designed to look for flares. Then you get flares. Ooh, nice. Give me that, thank you very much. So the noise for other people is our data. Probably the same thing. Right? They'll have like all the surveys can be potentially good / even excellent, because then you have more data. Although again, different flares, different stars, different thing. But having a better spectral coverage in a statistical way, it's always good. because the spectra I showed you, like GALEX is dead now, it's not working, right, for UV. The resolved spectra is from Hubble. So it's, you have to ask time, get time, wait for a flare to happen, so it's all by chance. So it's always case studies. So surveys, always good, always good.
Okay. Thank you. Another question is, I'm really ignorant, but I thought that there were quite a few satellites, telescopes in space that were looking constantly at the sun. None of them has spectrographer.
Excellent question. Not in the broad range, right? There are many ground-based and space-based spectrometers, but usually they are two things. They are high spatial resolution, so they look in a very small region in the sun, and very high spectral resolution, so the spectral window is tiny. So they look at magnesium 2 lines, or H-alpha, or calcium lines, and things, but they're very narrow. And it's sometimes, like the example I mentioned here from Lucia Client, it's too far? No, where is it? There you go. So this is ground-based from as a continuum near the helium-1 10830 line. So, oh, well, nice. There's a bit of continuum there. Cool. This is a side byproduct from the HMI space-based. It's a iron-1 line people use to get magnetic information from the sun. So, oh, nice. We have a continuum here as well. Let's grab that. And this is also the continuum part in the Balmer region near, oh, I forgot which line, but of course it's UV line that people observe with the IRIS telescope, solar telescope, same thing. It's very narrow band, so oh, there's a bit of in here. So it's usually like that.
Okay, thank you.
Yeah, no problem.
I have a physical question, because, you know, these white flares are probably mostly related to the feet of the gigantic loops in the corona that are doing the big X-ray solar flares, right? Really. So my question is, how can you, for instance, use the suns to follow up observation, knowing that there were a major flare the day before, or in other words, do you have any plans for, you know, combining observations of these white flares with events of large solar flares in X-rays, so that, because, you know, is there any plans in this direction, because they are certainly directly correlated?
They're correlated.
Question of hours or days, so.
No, they are simultaneous, right? These effects are always the same at the same time.
Exactly.
So, yeah. So it's always it's hard to know when a flare will happen. We can know more or less where, because of course you have these active regions related to the stronger magnetic fields, and by their configuration we can more or less know there's a higher chance of happening here instead of this one, for instance. But in terms of observations, it's always everything at the same time. Right? The white light stuff pops up at the same time as the X-rays and microwaves and everything. So let's say the strategy here is, when we look at what's happening in the sun at a given time. Let's say today all the clear skies we're going to observe. Okay, let's look at the sun, look at the magnetic structure. There are reports every day from a Maximilian, let's say, network that does reports every day. You get an email. Oh, there's the chance of solar activity in this active region or that, with coordinates and everything. So everyone that's observing can point to the same place. So if I get some data, let's say, hopefully, with suns we get the spectrum. Then someone in the US can get H-alpha line. And then from space, people can get the UV stuff. So we can combine all the data to look at what ends and from that falls.
And also collaborating these efforts.
Always, yes.
So, but So there are plans for this
Yeah.
follow-up
Yeah.
strategies.
Yes,
Okay.
yes.
More questions?
Feel free to ask any questions, curiosity questions. It's all absolutely fine.
Professor Paulo, thank you very much for the presentation. Very interesting.
Thank you.
I would like to ask, do you know exactly why people usually don't calibrate in intensity the spectra for the sun? For instance, those historical data?
Yeah. All right, I'll two things. For instance, right, I can get light curves. You saw the dynamic happening here, all the dynamics on the brightness will play. Yeah, right. I can get a light curve from this, so you get the intensity and the UV in this range. This is iron 9 line or something. Usually, people don't care about calibrating that because it's too much work, and the uncertainties will be like this because this is a kind of broadband-ish filter. Cool. Now, if we really want to, we can do it. Usually it's helpful for timing, morphology, and that stuff. Now, about this guy, this is more complicated. In principle, yeah, you can. We're gonna do this, right? You have calibration lamps, so you can calibrate in wavelength intensity, but then you have to account for all the bits in your telescope. How much light you're losing from the filter, from this beam splitter, from the mirrors, all in blue, in the red, so it starts to get shaky. It can be done. It's work, but it can be done. The other thing is, of course, we have a blue sky. Rayleigh scattering is a thing, right? So in the blue part, you have to account for that, and that's not straightforward depending on where you are. Again, São Paulo. So it can be done. We're gonna do it. We have to do it because that's the scientific objective of suns. Now, why these people didn't do it, I don't know. I really don't know. I would like to know. I know those people, and I asked the data. They send me that. I said, thanks, but how can you calibrate? Oh, no, yeah, well, yeah. Hope I answered.
More questions? No? Thank you again.
Thank you. Thank you. Thank you so much.
A gente tem agora um coffee break. Eu convido todos vocês. Muito obrigada. E um ótimo feriado a todos.